So in last lecture, we were discussing about a program in which we want to add 5 data bytes. We will quickly revise that program and we'll move further in the same program. The question was, write a logical program to sum sum 5 data bytes stored in memory location. The location was given 500H and store the answer in consecutive location. Okay, so there is a one space where we have stored the data that is starting from D500. From this point onward, we'll have 5 consecutive spaces like next to each other, where I have stored my data, and then in the next location, once I sum up all the data that I have there, I want to store the answer in next location. Okay, so this was the data. Let us assume this is the data. Okay, so what I'm going to do, I'm going to add this 99, 85, A6, 47 and 52, all the hexadecimal number, and I'm going to store the answer in D505. So that's the task that I have to do. Now to do that, in last lecture we have seen first instruction, that how I can read a data from a memory. So for that we have an instruction that is known as LDA, load from accumulator. What does that instruction do? That instruction basically will load a 16-bit like a data from given 16-bit address into your accumulator. Okay, so it will go to memory on this given address and it will bring in the data, whatever data is present at that particular address. For example, if I write LDA D502, okay, what I'm writing, LDA D502. In that case, it will come here, it will get A6 and bring that A6 into register A or accumulator. Okay, so that's the instruction. The instruction required 3 byte, 1 byte for the opcode itself, and the second and third byte is to store this 16-bit address. Okay, this 16-bit address will be stored in next two consecutive location of the like where the opcode has been saved. For an example, if opcode is saved on 2000, and then 2000 on 2001 address 00 would be stored, and on 2002 D5 would be stored. And the operations performed for using this instruction is first opcode fetch cycle, which will get the opcode of LDA and will understand that I have to bring in 16-bit address inside. So immediately it will go to the next two address and it will bring the 16-bit address, that is 00 and D5. Then once it get the address, it will perform a memory read cycle at the end, during which it will go to this D500 location over here, or D502 in our case, and it will bring whatever data is available over there into the accumulator. So actually there are 4 cycles performed during this instruction. First is opcode fetch, second is memory read, third is memory read, and fourth is again a memory read. Okay, so now let's start the program. The first line of the program will be LDA D500. So first I am bringing in my first data byte inside register A. Once I get this inside register A, we know that to perform the addition, I need accumulator and some other register. If I store two data in accumulator, for example, if I am moving 05 in the accumulator and then I am moving 10 in the accumulator, what it will do? There is only 8-bit space, so it will discard the old data and it will store the new data. So you have to take care that your data does not go away. So to perform that, what we have done? Once we bring in the number, first number, what we are going to do is we will be moving that number in some temporary register, or you can say the register B. Once I do that, then I can bring in my next number, that is 85. Okay, so now one number is in register B and the second number I am bringing in register A. Then I can perform the addition between A and B, and if I do that, first two addition would be performed. Now the answer of whatever this summation, whatever is the answer, that answer would be stored inside A. Now again, to bring in a new data, I need register A empty. So what I have to do again, I have to move that answer in register B one more time. Then what I can do, then I can again bring in my next data inside register A. Now as the answer is in register B, I can perform the sum between accumulator and B. Again, I am going to move that data to register B. Again, I'll bring next number. So this cycle goes on until you are completed with your data. So last data is at D50H, and then I am performing the addition, and here I am not moving the number. Okay, here I am not moving the number to register. Why? Because I know I have to store the answer in memory again. I know the location is D505. So what I'm going to do, I'm going to perform STA. What is STA? STA is the sister instruction of LDA. So LDA loads the data to accumulator from the memory, and STA will store the data in your memory. Where is STA? Not written over here. STA I have written it somewhere. Okay, no issue. STA will perform storing of data inside a memory. That means it perform memory write operation. So whatever is the answer in your calculator, it will go to this address and it will perform a memory write operation over here. So whatever is the answer will be written over here. So content of accumulator would be basically saved inside your memory. Okay. So right now my content is the summation of 5 data bytes, and if I perform STA, it will store that number. What are the cycles of what is the size of this instruction? Again, it's a 3 byte. 1 byte for opcode and second 2 byte are for this 16-bit address given over here. In the if you store 2000 opcode, then on 2001 you are going to perform 05 save 05, and on 2002 you are going to save D5. Okay. And at the last, I am stopping here. One more thing, the operation performed in ST instruction is first operation is same, opcode fetch. The second operation would be memory read. Third operation would be memory read again. For an example, for this example, first opcode fetch is okay, fine, good. Next memory read will be performed on 05 number. Okay, so it would be on 2001 location. Then next would be performed on 2002, again a memory read cycle. So combinedly it will get you the address, and once you get the whole address, it will go to the address and it will write the data. So third operation or fourth operation would be your memory write. So this 4 operation would be there. Instead of memory read over here, we'll get a memory write. Okay. So that's how we have done that program. Now at the end, I have told you that this program is wrong. Why? Because we haven't considered a carry. What is the status of carry? We haven't considered that, and that's why this is wrong. So where issue will be created? When you perform the sum between 99 and 85, at that time your issue will start. Okay. So once you perform the sum between these two numbers, 99 and 85, at that time your issue will begin. What would be the issue? You will get an carry over here, and if you do not take care about the carry, the answer or the result at the end you will get would be different than the expected result. Okay. I have forgot to install that thing. Let me check if it's available on my computer. Just a minute. Let me check online if we can get something. Won't be installed. Okay, we have one. This one. What I'm going to do, I'm going to dump this code over there. So this is the space where I'm going to write my code. And then I will try to compile. Finish compilation in 4 milliseconds. Okay, done. That's what, no issue. But before we start, I have to store the data in this given location, okay, D500H onwards. So let's go there. Okay, we have this address D500 over here. Now I'm going to store some numbers, let us say 10, 20, 30, 40, and 50. Okay. Now see what I have done. I have stored some number over here. This is the location D50. This is D500. Okay. Then the next just beside it is D501, 2, 3, 4, 5, 6, 7. Then D508 on the next line. Okay. So the first address is given of the rows. And if you go to like next column, it would be the next address. So this is my D500, D502, sorry, 1, 2, 3, and 4. I have stored 5 numbers over there. And now let us try to compile this code. And if the code is correct, we will get the answer over this step. Okay, instead of 00, I'll get my answer. Okay, let's compile this. I have to again go to this given address. I have to store it again. I have pressed the wrong number. Okay, now let us see. I'm going to run this code. Okay, now let us see. It is like that. Once I compile this thing, it moves away like. I haven't used this compiler. That's the issue. Otherwise, it won't be an issue. Let me try it one more time. Don't know, somehow the data vanishes. Uh, just a moment. What I'm going to do is I'm going to store the data using program itself. Okay. See what I have done. I have first moved 10 in one register, that is register A. Then I am storing that 10 number on D500, D51234. So all the location I am going to store the 10. So I'm using this program itself to store the data in the memory. Okay, so that's not how we do that. But for time being, I'm doing this because just what we need is the understanding of the program, whether the program is correct or not. So I'm going to compile this code. Now if I go to this address, it's still empty. I don't know why. Might be this capital or small is the issue. Once I put this code inside your inside this, it should be 10 should be appearing here, but I don't know why it's not appearing. Let's try the other location. We are not doing this. Let it be. I'll get you the correct compiler and then I'll show you. But what basic issue according to this program is it is not considering a carry. So what will happen? What will actually happen? Let's see it using a calculator. I can explain you what is going to happen. Okay. So I'm going to hexadecimal system and my first number is 99. See, I'm going to perform the addition. So 99 plus 85. Now the answer is 11E. Yeah, go ahead. Hello.
Yes, sir. Done.
It will take a time to see the calculator. Okay. So what I am going to do is I am going to write first answer over here. My first answer is 11E. Okay. But what will happen as your accumulator is only 8-bit register, it will see only this part. So 1E is stored inside your accumulator and now you are performing the addition between this 1E and the next number, that is A6. So first you have performed this 9985, you get 11E. This one is stored inside accumulator. We are moving that to register B. So now your B holds 1E and you bring in the next number, that is A6 inside your accumulator. So what you are going to do is you are going to discard this carry yourself. There is no error from 8085, but you are creating that error. How you have created that error? You have created that error by ignoring that carry. So now what you are going to do? You are going to perform addition between 1E and the next number is A6. Okay. So you are going to perform the addition between these two numbers. You will get C4. So C4 would be stored inside your accumulator now. So C4 is the next answer. Then you are going to add C4 with 47. Okay. There is no carry now, so don't worry about that. I'm going to add 47. Again I get 10B. Again your accumulator will only see this 0B, and then 52 would be added to this 0B, so you'll get 5C somewhere. Okay, so at the end, when you store this accumulator using STA, what you will get here is only the number 57. You get only this. Okay, so what is missing? The carry is missing. We have generated query twice, so instead of 57 it should be 257. Okay, the actual answer would be 257. Let's check that. 99 plus 85 plus A6 plus 47 and 52. What is getting 250D, 25D. We should have taken something. Yeah, it should be 5D only itself. Here it's wrong. It should be 5D. So the actual answer is 25D. Why I have written 57 over here? It's 5D. What you will get is 5D instead of 25D. So this 2 is missing and that error is generated by you as you have not considered the carry. So how you can consider a carry? That's first question. Like how you can see whether the summation get me a carry or not. How to do that? To do that, you have one special register, and that register is known as flag register. Okay. So there is another register named as a flag register. There is this register known as a flag register. what this register will do, or what is the size of this register. This is an 8-bit register. Okay, let's check it out in your book where it is given, and even I don't have to draw the figure in that case. Your here, chapter number 2, and your page number, no, 32. On page number 32, you have given this. This is the page. This is the page. It won't go. So here you can see this register is a flag register. This is a flag register. This is a flag register. Okay. We will snip it out and we'll take that register to your notebook so I can explain it. So see, this is a flag register. Now, what are the various bits of flag register? So this is a 8-bit register, but what are the 8 bits? So these are the 8-bit. Okay, starting from this D0, that is LSB, and this is MSB. What are these various bits and how that bits are useful? That's the first question. So this register is basically storing the some important information about the arithmetic when arithmetic and logical operations performed at that time. Some important information is generated, and this register basically stores that. And based on this register status, you can take some decision. For an example, let us start understanding this register. The first bit of this register, or known as LSB, is CY. What is CY? CY is nothing but your carry bit that we were looking for. Okay, so if you perform this operation between the first two number, your first two number, that is 99 and 85, okay, 99 plus 85, as soon as you perform this, your answer is 1E. You know that. But this 1E would be stored in accumulator. So where is this carry will be stored? This carry will be stored inside your carry registers. Okay. So as soon as you perform the addition between these two numbers by writing the instruction add B, once this instruction executes, your accumulator holds 1E and your carry flag, this flag, or at this point, you get 1. So inside your flag register, the status of your carry bit will be changing to 1. Okay. So this is a carry bit. It will hold the important information. What is the important information? It's just status of carry. If if carry is generated, then carry bit will become 1. If carry is not generated, in that case carry will is 0. Or you can say carry reset, and when it becomes 1, you can say carry is set. So if you perform the operation 05 plus 05 or 01, in that case your answer would be 06. Again, 06 would be stored inside an accumulator. But if the status of carry flag is previously 1, it will reset it to 0. If it's 0, it will again reset it to 0. That means along with storing this answer in the accumulator, it will also modifying the status of carry flag. Whether be it 1 or 0, it will try to reset it one more time to make sure your answer stored is 006 and not 106. Okay. So every time you perform arithmetic operations or you perform logical operation, in both this case, your carry flag can modify depending on the instruction you use. Okay, like it's given inside the instruction. When you read the instruction at that time, it would be given which are the flags it can modify. So carry flag is such flag which will be most of the time will be modified. be it arithmetic, sometimes it is used in logical operations as well. We'll see some logical operation where the carry flag is modified. Okay, so this is the basics about carry flag. Now, what about the other this bits? What are the other bits? So you understand carry bit now. The next bit is parity bit. Now, how a parity bit works? So if your answer, for an example here, my answer is 1E. So it is actually storing the information about a parity. Okay, so 1 is in binary. I can say 001, 001, and E is 1110. So this is the answer inside an accumulator. What parity bit will store? Parity will bit will store the information about number of ones inside your answer. So here you can see first one, second one, third one, and fourth one. So there are 4 ones. That means that's even parity. Okay. If your answer is like this 0 1 0 0 1 0 0, in that case you will get 3 ones, and that's odd parity. Okay, so if your even parity is there, then your parity bit will reset, and if the parity is odd, okay, or you will get odd number of ones in your answer. These are odd numbers of ones. 1 3 5 7 is the odd numbers. Okay, and if you get this odd numbers of ones, in that case your parity will set. Okay, so this is how a parity bit works. Now you might think where this kind of information is useful. This kind of information is useful when you are performing a communication. So if you are performing a communication between two devices, and if you want to check whether whatever the answer is transferred, okay, whether the receiver get the correct answer or not. So if I'm sending 0010, and if I'm receiving 0110, and if I check parity of this and this, you'll get different parity. So this is very basic element, or like very basic method. Okay, it might get the wrong answer as well, like it's not 100% sure. Okay, you will always get the correct error, but earlier when that algorithms were not so good, at that time the parity check method was used. Okay, so in that case the parity won't match. For here the parity would be odd, or you will get parity as a 1, you will get parity as a 0, and it won't match. So you can say the communication taken place was wrong. So this kind of check can be performed using parity bit. Okay. Detail explanation is given inside the book itself. You can read it over here. Okay. See, this is a flag register. So here all the information is given. If the result an even number of ones, the flag is set. Sorry. It is different. If the odd numbers of one, it will reset, and if the number of parity is like even numbers of ones, in that case it will set. Okay. It will set when your parity are even, and it will reset if your parity is odd. Then the next are given, but let's see that personally. Then there is AC, auxiliary carry. Now what does this mean, auxiliary carry? So let's have an example for an auxiliary carry. Let's say I'm performing an addition. I should have one over here. And there is one more number 001 1001. So see, these are the two numbers. So I am going to perform addition between these two numbers. 01 is 1, again 10 is 1, 00 is 0, 1 plus 1 is 0 with 1 carry. So if a carry moves from this place to this place, what is this place? This place is known as D3, and this place is known as D4. Data bit 3, data bit 4. So data bit, this is my data bit 0, and this is my data bit 7. So that are the 8-bit numbers. So it looks like this: D0, D1, D2, D3, then D4, D5, D6, and D7. So if a carry bit moves, a carry is generated at this position and it is moved to D4, okay, or due to the number present on D3, if a carry is generated at D4 place, at that time your auxiliary carry will set. And if here you have 0, and in that case the carry won't be generated, you get 1 over here and carry generated would be 0, like no carry would be there. in that case your auxiliary carry will reset. So if a carry is carry forward from position D3 to D4, in that case your auxiliary carry flag will set, otherwise it will reset. Okay, so see, if a D3 pass to D4, a carry is generated from D3 to D4, in that case this will set. Now when this might be useful, this will be useful when you are using BCD numbers, binary coded decimal, where you will have 0 to 9, then 10 to 19. So you won't have A, B, C, D over there. At that time, this auxiliary carry is very helpful to convert this hexadecimal numbers to BCD numbers. It is helpful at that time, but we are not going into that, so not in detail. But this can be asked. Draw these flag register and explain all the bits of flag register. In that case, you have to explain all these bits. At that time, this information will be useful. You can give this kind of example as well. Okay. Now let's talk about the last two. The last two is sign flag and zero flag. Okay. S is for sign flag and Z is for zero flag. Okay. So when zero flag will set, when it will set and when it will reset. So it will set if your answer is 0. That means let us have instruction add B. Now let's have the content of accumulator was 1 9 and the content of register B was let us say 9 plus 6 15. Okay, so 6, and here I will have 9 6 15 is F. Okay, so let us say 7. 1 plus 1 2 14 16. You should have an F or E over here. So if you have this kind of numbers 19 and E7, let us try to add that two numbers, 19 plus E7. So I am going to add 19 plus E7. What I will get is 100. Okay. So if I perform this operation, excuse me, sorry for that. So if you perform this operation, your accumulator will hold the number 0 0, your carry flag will set to 1, so combinedly it makes 100. But right now the result, if you talk about the result is 0 0. See, in this kind of scenario your carry flag will set. If your answer is 0, then and then your carry flag will set. But if your answer is, let us say, 0 1, in that case your answer is not 0. Is it 0? No. In that case your 0 flag will reset if answer is non-zero. So there would be very few times when your zero flag is set. Most of the time zero flag would be reset. So what do you mean by zero flag set? So see what will happen if your answer is actually 0 0, at that time your Z will become 1. If your answer is other than that, in that case zero flag will reset. This is very simple logic. At any point of time, whether be it addition or subtraction, if your answer is 0, then 0 flag will set. Okay. Now let us discuss about the last one, that is S, or you know it as a sign flag. So right now, whatever operation we perform is what kind of operation? Unsigned. I am not at all bothered about whether the number is positive or negative. What I have considered is all the numbers that I am going to write are positive numbers. But it's not the scenario. Sometimes you might be required to perform the signed operation. Okay. So if I discuss about the signed operation number, the number would be starting from negative 128 in case of decimal up to positive 127, or else the number would be in hexadecimal. If I say, it would be positive numbers would be starting from 00H and it will last up to 80H, and negative number will be starting from FFH or let us say 81, sorry, it is 8f, 7f, and here it will start from 80 and it will go to ffh. These are the negative numbers. Now why I am saying this is a negative number? So the general rule for this sign flag is sign flag, or in 8085 according to the sign number operation, if you are performing if you have any number whose D7 bit is 1, then that number is negative. If you are performing sign operation then and then, okay, otherwise if D7 bit is 0, that's a positive number. That's why I'm saying this 00 to 7f is the positive number. So 00 is this number, so this is 0, that's why it's a positive number, and 07f is this number. So again 0 is there on the MSB, so this is also a positive number. So 80 is this number, so this is a negative number, this is a negative, but which number is negative, which number? So that depends. Okay, same way if I write ff, again that's the negative number. Okay, so what a sign flag do? Sign flag will reflect the sign of your number or answer, rather answer. Okay, how it will do? It will just take the D7 bit and it will paste it over here. Okay, so if you get 0 in sign flag, that means number is positive. If you get 1 in sign flag, that's number is negative. How it is going to do that? It will copy the content of D7th bit in answer. Okay, so if your answer is, let us say this 100 0001100, what it will do? It will take this bit and it will store inside a sign flag. So sign flag will become 1. That means this is a negative number. That's how a sign flag works. Now immediate a question will occur, then how negative number are stored. Okay, let us say I have to store a negative number, that is 2. I want to store -2 inside my 8085. Then how can I store that? So negative number is always stored in 2's complement format in your 8085. Okay, so what's 2's complement? So you know, if your number 2, that is basically this number -2, but I'm not at all considering right now negative because this is a decimal, so I'm going to convert it to hexadecimal. And then I'm going to as this is a negative number, to represent the negative sign you have to convert it to 2's complement. So first I'm writing the number 2, that is 0000010. Now you know that to convert that number in 2's complement, first you have to find out the 1's complement. How to find out 1's complement? Take all the numbers opposite, like if it is 0 make it 1, if it is 1 make it 0. Okay, so 10001, that's my first complement. Then how to find the 2's complement? Add 1 to the answer or 1's complement. So I'm going to add a 1, and what I'll get, 1 plus 1 is 0 with carry 1. Okay, then no numbers are over here, so 1 added to 0, again I'll get 1, then no numbers over here, so it will get 0 0 0. Sorry, so there is something wrong with that. I am not getting this. The number is 411101, and I'm going to add 1 to that number. So what I will get is, yeah, correct, I'm getting this. 1 plus 1 is 0, 1, 11, and all ones. I don't know why I have written 0 over here, but all ones. So this is the number that I will store. So in hexadecimal, what is this number? That is F, and that is E. So if you store FE in your 8085, that means you have stored a -2 in decimal. Okay, so this kind of question can be asked in MCQ. What would be the number, how number -5 is stored inside the 8085? 5 options will be given. One would be 1's complement, the other would be 2's complement, one would be directly negative number with 1 sign. But actually how it is done, if you have a negative number, convert that number itself into 2's complement, And once you have that number in 2's complement, it's a negative number itself, so you do not have to worry about sign. Okay. Now if you look at this number, see, you have this one, the sign flag is 1, that means it's a negative number. Okay, so this is how flag register works. So flag register gives you inside information of various bit during operations. Okay, then the very first question, when this will modify, like who is going to modify it? This will be modifying itself depending on the result. So whenever you perform arithmetic or logical operation, at that time the carry flag, parity flag, auxiliary carry flag, zero flag or sign flag, depending on the instruction, will modify itself. You do not have to worry about it. What you have to worry about it, whether the carry is set or not. Like that's kind of question that you would be asking. It will reset itself, no issue. But if it's a set, then you have to take care, because a carry is generated and you have to take care of that carry. Clear? If you have any question in this flag register, you can ask, or we will move ahead. Okay, if you don't have any question, no issue, I can move ahead. And now what we are going to do, we are going to modify this program. We are going to modify this program, and we'll be taking care of the carry that has been generated during the program. Okay, so I'm going to copy paste this program at the low level, and then we can begin from here. This is my program, and I'm going to modify this program, okay, to check whether a carry is generated. If yes, then we'll take care about it. That's the task we want to do. Okay, so let us first take an example, a very simple example, how you can check for a carry. Now, to check for any carry or any other register, let us say zero flag or carry flag, to check the status of either a carry flag or a zero flag, there are a special kind of instructions. There are a special instruction which can do that. Otherwise, there is no other way to do that. There is only a special kind of instruction. Which kind of instruction are that? That are a very special. Which is the type? I will say that's the branching operation. And using this branching operation, only you can check the status of the carry flag. So our very first question is what are the branching operations? So branching operations are the one which can skip the part of program or jump forward or backward kind of thing. So what exactly I mean is, if I'm executing this instruction, I'll be immediately branching from here to here or somewhere else. Okay, I can perform a forward jump or backward jump. So this is a branching operation. I am not going sequentially now. What I am doing, there is some occurrence where I have to jump, and what I am doing, I am skipping part of program either in forward direction or backward direction. So this is a branching operation. Okay. Okay. This kind of information, like this kind of operation, are very basic operations, and it may be needed in a lot of times. We are going to see one example of this operation. Okay. What we are going to do is, first we'll explain this operation using this very first two element 99 and 85. So let us say you have been asked a new program. I'm going to come back to this program again, but for time being, let us assume you have been given two numbers 99 and 85, and you want to add that two numbers, and you have to check the carry and store the carry if available. This is the task given. Okay, the content is stored in A, B, answers should be stored in register D, and if carry is there, carry status should be stored in C. This is the task. So your A and B holds the number, or you have to move that number over there. How to move that number? We know that how to do that. The instruction is MVI A, comma 99H. What this instruction will do? It will store number 99 in register A. Size of this instruction 2 byte. Operation perform 2 operation, opcode fetch and memory read. Next operation I am going to store the next number, that is 85. So MVIB, comma 85H. Once I have that two number, I can add that two number using add B. Once you do this, your answer is stored in register A. What is your answer? Answer is 11E. 11E. Actually, your answer is 1E, and your carry flag would be 1. Okay. So how can I store the number? I can store the answer in register D by moving the content from A to D, and then I can stop. If you done this, your program is half correct, but the carry status is still missing. And during this operation, we know that carry is generated. So how to take care of this carry? Then I'll go to this branching operation. So what are the basic branching operation? There are two type of branching operation. First are conditional branch, or let us say not conditional branch. Let us say branching operations mainly have two type of operation. First is jump operation, and second one is call operation. Okay, what you will do? Jump operation, depending on some situation, you will perform a jump. Okay, jump can be of two types now: a conditional jump, and the second one is unconditional jump. What are the example of conditional and unconditional jump? A conditional jump is one in which uh, according to some condition you will take the decision whether to jump or not, and in unconditional jump, without taking care of any decision, you will jump. So there are just two kind of jump available in your 8085. For an example, you are making noise in the class without any like any joke or anything, then that's the unconditional. A conditional, if I crack a joke and you are laughing, then that's the conditional laughing. That's kind of thing. If there is a condition, if condition is true, then you are going to do some task. If condition is false, that you are not going to do some task. In unconditional, whether the thing is true or not, you are going to jump. Okay, so let's have an example of both of this. Unconditional jump looks like this. It is written as JMP followed by 16-bit address, and the conditional one is this: JC, JNC, JZ, and JNZ, where your Z represents 0 and C represent a carry. I'm going to details inside this. This is again a 16-bit operations. Like 16-bit address would be there followed by that instruction. Okay. So all this instruction would be a 3-byte instruction, and we are not going into the what are the cycle perform, because uh, that's a different thing. Okay, so let me give you one more hint. Sometime it's a 70 state. I'm not going to discuss the cycles because it is a bit controversial, but let us assume this. Uh, at one when you have to calculate the time, at that time this information would be needed. A 70 state and 10 state. 10 state if jump is performed. 70 state if jump is not performed. That's the only information that you need. Otherwise, the timing diagram of this is not, it cannot be asked. What are the operation performed? That cannot be asked. If I ask that what are the operation performed, generally it is opcode fetch followed by 2 memory read, because this is 3-byte instruction. How this instruction would be written? So if 2000 is the address, first would be the opcode and second two would be the addresses. Which addresses? Given by this 16-bit address. Like it would be this 16-bit address, first LSB and then MSB. That's the type of instruction is written. But what does that mean? What this jump or JC or JNC or JZ and JNZ means? Jump, a very basic jump, JMP, is an unconditional jump. So if I write jump 2000, let us have an example over here. Let us say this is the address like 2000, then 2001, 2, 3, 4, 5, 6, 7, 8, 9 A B C D. Let us say this is 2000 D. Actually it is 2000 D. I have calculated this. So if I write over here, if instead of move I am writing JMP 2000 D, what it will do? It will execute this. It will come here. It will see jump 2000 D. Without checking any condition, it will go here. It will skip all this program. Okay, it will directly go to the location 2000 D, and it will start executing from this line onwards. That's the jump. Without any condition, it will jump because it has seen JMP. That's why it will only jump, unconditional jump. But the JC and JNC are a bit sensitive, and that will jump depending on the condition. JC will perform a jump if carry is generated, and GNC will perform jump if no carry generated. So that two are different. So at some time you might need JC and sometime you might need GNC. That depends on situation to situation. Okay. So how does this work? So let us have an example over here. So if here instead of this move DA, instead of this move DA, if I have written, let's JC to some address. Okay, right now we are not discussing how to write address, but let us say I have written JC some address, and let us say address is somewhere here. There is some other line of code, and here there is a code which says move C, D, something like that. So if this line of code is executing, at that time this JC will occur. What this will do? This will jump or not? That is the first question. Whether this jump will be performed, like program will go from here to here, or it will take this turn. This is option A, this is option B. Can anyone tell me what would be the option it will take? This is a program, and what would be the result? Option A or option B? Now, how to decide that? That can be decided based on the result. So we know that here, when the result is generated, at that time, by looking this number, you can take the decision that carry was generated, and your answer, whatever was the answer. I'm not interested in the answer, but the thing is carry is generated. So this is jump on carry to this address. So carry is generated. Yes, carry is right now 1. So what it will do? This instruction jump on carry. So yes, it will jump to this address. So it will take option B and not option A. But instead of that, if you have written GNC here, jump on no carry, but carry is generated, that means it will false. That condition will be false, and it will go immediately to the next instruction over here. So if you have written GNC instead of JC, it won't perform jump. But if you have written JC, then it will be performing a jump. Okay. Now we'll discuss about this in next lecture because it's 10:06. We'll stop here for today's lecture. If you have any question, you can ask, or you can leave.